Welcome to Independent Aircraft Investigations. My name is Richard Godfrey. Today we are going to investigate the crash of TWA 800. Was this event predictable and preventable? TWA Flight 800 crashed on the 17th of July 1996 at 20:31 Eastern Daylight Time, and just 12 minutes after takeoff from New York JFK Airport. It crashed in the Atlantic Ocean just 7 nautical miles off the coast of Long Island. All 212 passengers and 18 crew were killed. The NTSB, the FBI, the CIA, and the New York Police Department all investigated. The National Transportation Safety Board determines that the probable cause of TWA Flight 800 accident was an explosion of the center wing fuel tank, the CWT, resulting from ignition of the flammable fuel-air mixture in the tank. The source of ignition energy for the explosion could not be determined with certainty, but of the sources evaluated by the investigation, the most likely was a short circuit outside of the CWT that allowed excessive voltage to enter it through electrical wiring associated with the fuel quantity indication system. The final report, which was 341 pages long, documents the NTSB accident investigation, as well as the role of the FBI and the CIA in their criminal and terrorist parallel investigations. In total, 58 organizations were involved with the investigation, and that included 25 universities and research laboratories. Aviation safety is a team effort between aircraft design, manufacturer, operation, maintenance, regulator, and accident investigators. Here is a disclaimer. Not all 736 FBI witness statements have been publicly released. However, the available physical, structural, and forensic evidence provides a comprehensive basis for analysis. Families of victims filed hundreds of wrongful death claims, which were settled out of court for an estimated $500 million. Subsequent Freedom of Information Act litigation has led to the release of some of the CIA and FBI material that was not publicly available at the time of the original investigation. Aviation investigators and regulators overwhelmingly accept the center wing tank explosion as the cause of the accident. Courts have not accepted alternative causation theories, and mainstream scientific and engineering analysis is aligned with the findings of the NTSB. Some victims' family members, as well as former investigators and technical professionals, independent researchers, and journalists, continue to dispute the NTSB's probable cause determination. The NTSB case is well made, but the FBI and CIA seriously investigated both a missile attack and a terrorist bomb attack. In preparing this analysis, I've listened to the families of the victims, former TWA pilots, and individuals involved in the investigation. This is not an abstract case. It is one that still matters deeply to the people connected to it, and this discussion will continue. The CIA produced a reconstruction to explain eyewitness reports of a rising object. That reconstruction has been debated and criticized in some quarters, but the underlying question still remains open. How do we reconcile eyewitness perception with the physical evidence? The FBI investigation involved over 2,000 personnel and collected 736 witness statements. Many of those are from trained observers, such as military and commercial pilots. Many of those witnesses were confident they observed a rising object consistent with a missile. The investigation, therefore, had to reconcile those observations with the physical and forensic evidence recovered from the aircraft. The challenge was not to dismiss those observations, but to determine whether they were consistent with the physical evidence. The TWA800 investigation exposed in a very visible way aviation safety is not a single entity's job. It's a system of interacting roles, each with different authority, incentives, and limitations. Let's break it down in a structured system-level way. Firstly, the big picture, the aviation safety system. You can think of aviation safety as a closed-loop system. It goes from design to certification, to operation, to monitoring, to failure, to investigation, to recommendation, regulation, design changes, and then your full circle back to the design. And each actor sits at a different point in that loop. What are the core roles and responsibilities? Firstly, the regulators like the FAA or the EASA in Europe. Their primary role is to set the rules and enforce compliance. Their responsibility, the certification of aircraft. They approve designs with type certificates, and they issue ADs, airworthiness directives, which create the need for mandatory fixes. They also issue NPRMs, Notice of Proposed Rulemaking, and that's when they want to bring in future regulations. The reality, as the TWA800 accident shows, regulators often react to data and pressure. Many issues existed decades before the accident. There were fuel tank explosions. There was wiring degradation. And action can be slow. 13 years of history prior to the TWA800 accident and 10 years after the accident to solve all the issues raised. It can be incremental. There are working groups and committees with point solutions. And it can be risk-based rather than hazard elimination. You get to hear if it is extremely unlikely, we don't need to worry about it. In TWA800, the FAA had prior knowledge of fuel tank flammability risks, but no requirement existed to eliminate ignition risk or make fuel tanks inert. Secondly, the investigators, NTSB, AAIB, Bayer. Their primary role is to find out what happened and why, not to assign blame. And their responsibilities determine the probable cause of an accident, identify systemic failures, and issue safety recommendations. They analyze the design, the maintenance, the human factors, and organizational behavior. The key constraint they have is they cannot enforce anything. The NTSB investigates accidents, issues recommendations, and evaluates safety effectiveness of the agencies. The critical insight: investigators are the only body looking at the entire system end to end. Then there are the manufacturers and suppliers: Boeing and Airbus and GE and Rolls-Royce and Pratt and Whitney and CFM. Their primary role is to design and build aircraft and engines and systems. Their responsibilities: the aircraft system design and compliance with certification rules. They issue service bulletins, SBs, with recommended fixes, and they support operators and regulators. The reality: they design to the certification standard, but not beyond it. Certification assumptions may become outdated, and they may miss failure modes. For example, in the case of TWA800, aging of wiring in aircraft. The fuel tank ignition risk existed in design assumptions, and the wiring separation and protection standards were insufficient. Then the operators, airlines like TWA, their primary role: to operate aircraft safely within the rules. Their responsibilities: flight operations and maintenance programs. Compliance with ADs, mandatory, and SBs, optional unless mandated. Reporting issues via SDRs, service difficulty reports. The reality: airlines operate under cost pressure and schedule pressure. Maintenance programs are approved by the regulator and often based on manufacturer guidance. But on TWA800, maintenance actions near the fuel quantity wiring were examined, and they reveal how routine maintenance can interact with latent design risks. So let's think about the safety information flow. This is a continuous data loop. Operational data from SDRs, incident reports, and airline internal findings. Manufacturer analysis and trends and service bulletins are issued. Regulator action, MPRMs and ADs, the mandatory fixes. Implementation data: airlines comply, maintenance is updated. And then if the system fails, there are accident and failure. So in this case, the NTSB investigation. And finally, they make safety recommendations and feedback into the regulator and the industry. So TWA is actually a textbook case of why problems persist. The report shows issues dating back to 1967. Fuel tank explosions were known. Wiring degradation was known. Flammability risks were known. Yet no systemic fix until after a major accident. Why? First reason: responsibility and ownership. No single entity owns the hazard. The FAA regulates but doesn't design. Boeing designs but meets regulations. Airlines operate but don't redesign. And the NTSB can recommend but cannot enforce. The second is risk normalization. Rare events are tolerated. Acceptable risk becomes embedded. Then there are economic and operational constraints. Retrofitting fleets is expensive. Changes require regulatory justification. And finally, the certification philosophy. Historically, that was prevent ignition sources. Then it changed with TWA 800. And currently, it is eliminate all flammable conditions. And TWA 800 forced a shift. The hazard was identified in 1967, but only after 1996, when the accident happened, did regulators accept that ignition prevention alone was insufficient. By 2008, fuel tank flammability reduction, typically via nitrogen inerting, became a mandated design requirement, significantly reducing, but not eliminating, the risk. So what changed after TWA 800? The investigation triggered system-level corrections. There were regulatory changes, new fuel tank safety rules, flammability reduction requirements, design changes, nitrogen inerting systems, better wiring separation and protection, maintenance changes, the aging aircraft programs were introduced, enhanced wiring inspection standards, and improved oversight, more proactive hazard identification. The key insight from all of this: the aviation safety process can only work as a team. No single actor is sufficient. Safety emerges from the interaction of all of them. Most major accidents occur when each actor fulfills its role, but the system as a whole fails. Independent aircraft investigations analysis of the TWA 800 is as follows. Models like the Swiss cheese model and the black swan theory are useful, but they don't fully capture what happened here. This was not simply a random alignment of failures, nor an unforeseeable event. It was the manifestation of a known hazard that persisted across decades without a systemic solution. Individual accidents are not predictable in their specific time, place, or aircraft. However, accident classes that arise from known hazards are both predictable and preventable. In the case of TWA Flight 800, the hazard of fuel tank explosions in transport aircraft was well known. Issues of fuel tank flammability, potential ignition sources, design assumptions, and aging wiring have been identified over decades. Therefore, while the specific accident involving TWA Flight 800 was not predictable, a fuel tank explosion of this type was both predictable and preventable. The accident represents the realization of a known system-level hazard that had not been effectively mitigated. Let's look at the certification issues. The certification assumption was explicitly probabilistic. Transport category aircraft certification under FAA rules like paragraph 25.901 and 25.1309 relied on the statement ignition sources inside fuel tanks must be extremely improbable. In practice, this meant there was no requirement to eliminate flammable mixtures and no requirement to make fuel tanks inert. There was a reliance on wiring separation, component reliability, and redundancy. So the system was built on a probability argument, not an elimination of risk. And known pre-1996 evidence contradicted that assumption. There was documented ignition capable failures before TWA Flight 800. Philippine Airlines Flight 143, for example, a confirmed electrical energy entered a fuel tank. Multiple service difficulty reports in the FAA database, arcing wires, fuel pump faults, indication system anomalies. These directly challenge the extremely improbable. Flammability was routine, not rare. Center wing tanks, especially on 747s, sit above air conditioning packs, get heated during the climb, often partially empty, and the result, the ullage frequently within flammable range. So one leg of the triangle, the flammable mixture, was not rare at all. It was expected. Then ignition energy thresholds are low. Jet A vapor ignition requires relatively low energy, easily achievable by wiring faults, static discharge, or pump operation anomalies. If energy ever gets into the tank, ignition is plausible. It's not extraordinary. The system had no true independence. The probabilistic model assumed failures are independent. Barriers are separate layers. But in reality, the fuel quantity indication system, the FQIS wiring, the power wiring, the aging insulation were often physically co-located, electrically coupled under fault conditions. This creates common cause failure paths, which invalidate probability and multiply the risk. The risk increases dramatically. Aging aircraft effects were underestimated. The 747 involved in TWA800 was 25 years old, and the aging effects included insulation breakdown and contamination and maintenance-induced damage. At the time, aging wiring was not well modeled, and failure rates were assumed to be closer to new aircraft conditions. So the probability inputs themselves were optimistic. No consequence-based safety design. Even if ignition occurred, tanks were not designed to tolerate explosions. There was no explosion venting, no structural isolation, and no inerting. So a single failure could escalate directly to a catastrophic structural breakup. That violates a core safety principle. Avoid single-point catastrophic failure modes. Let's have a look at the risk assessment. Regulators like the FAA didn't just fix a component, they changed the whole philosophy. The new approach was to assume ignition sources will eventually occur, reduce flammability exposure with inerting systems, not just ignition probability. This is a shift from probability-based safety to physics-based risk elimination. So was it predictable? Not predictable in the sense of this exact aircraft will explode on this date, but predictable in the sense of the system contained frequent flammable conditions, known ignition pathways, weak independence assumptions, and no mitigation if ignition occurred. That combination makes the event statistically unlikely in the short term, but structurally inevitable over a long enough exposure. Calling TWA800 a predictable failure masked by flawed probability assumptions is a justified statement because the risk factors were known and present. The model used to dismiss them relied on invalid assumptions. The system lacked defense in depth. So the accident wasn't a complete unknown. It was a low frequency, high consequence failure that the framework failed to properly capture. Now let's have a look at the flight path analysis. This is where it starts to get really interesting. The TWA Flight 800 was holding at 13,000 feet from 2027-47 EDT to 2030-35 EDT, when the flight engineer acknowledged climb thrust was applied. At 2031-12, the aircraft was ascending through 13,760 feet when the accident occurred, and the FDR stopped recording. The captain's altimeter was found indicating 13,820 feet, and the first officer's altimeter was found indicating 13,800 feet. The climb was from 13,000 feet to, say, 13,810 in 37 seconds. This represents a climb rate of 1,313.5 feet per minute. The weight of the aircraft on takeoff was 590,441 pounds. At 2031-12, the aircraft had used 10,960 pounds of fuel. So that leaves the aircraft weight at that point in time at 579,481 pounds. The typical climb indicated airspeed for a Boeing 747-100 at climb thrust and the aircraft weight of 579,481 pounds and the outside air temperature of minus 3.6 degrees centigrade at 13,000 feet is 302 Kias. The TAS, the true airspeed, was 371 knots, and the ground speed was 386 knots, given the wind of 16 knots from 290 degrees true. The radar data from the civilian aviation radar are not designed to detect missiles, but some military radars are designed for that purpose. Civilian radar data must also be interpreted carefully. Primary and secondary radar systems are not designed to reliably detect small, fast-moving objects like missile bodies, particularly at low altitudes or outside of optimal coverage. However, no radar data has been shown to provide a consistent track or signature supporting a missile engagement. The crash area is divided into three zones: the red zone, yellow zone, and the green zone. The distance from the last transponder point at 40.65 degrees north, 72.67 degrees west, to the midpoint of the red zone is only 1.7709 kilometers, or 0.9562 nautical miles, on a track of 121.5 degrees true. The distance from the last transponder point to the midpoint of the yellow zone is a bit further, 2.4661 kilometers. That's 1.3316 nautical miles on a track of 88.7 degrees true. And the distance from that last transponder point to the green zone midpoint is much further, 4.7924 kilometers, 2.5877 nautical miles, and on a track of 78.6 degrees true. Let's have a look at the debris evidence. The initiating event was the center wing tank explosion. Subsequent breakup involved structural failure and extensive fuel-fed fire, particularly on the right wing. But the NTSB did not find that the aircraft was destroyed by a chain reaction of separate left and right wing tank explosions. There is one very noticeable feature in the debris evidence. The air conditioning packs, which there are three underneath the center wing tank, Pack 1, which is on the left, and Pack 3 on the right, were found in the early red debris field, while Pack 2, the center line, was recovered from the later green main wreckage area. Given that all three packs are located directly beneath or adjacent to the center wing tank, this distribution indicates that the outboard portions of the lower fuselage separated earlier than the center structure. This pattern is consistent with an initial structural disruption in the center wing tank and the pack bay region, with failure propagating outward across the lower fuselage. However, the exact local failure mechanism, whether dominated by explosive overpressure effects or subsequent progressive structural failure, cannot be determined from this pack distribution alone. Let's consider comparable events. A structured comparison of known accident cases provides a useful framework for evaluating the competing hypotheses for the destruction of TWA Flight 800. In particular, we looked at two accidents, the Itavia Flight 870 and the Malaysia Airline Flight MH17, and illustrate the characteristic physical signatures of respectively an onboard explosive device and a missile warhead. These can be compared directly with the observed structural and debris evidence from TWA 800. Firstly, the internal explosive device on Itavia Flight 870. Technical analysis of the Itavia DC-9 wreckage identified a localized region of severe structural damage centered in the rear starboard toilet. The deformation pattern showed violent outward displacement of the surrounding structure, highly localized structural distortion concentrated in a confined volume, and damage consistent with the discrete source of high energy and internal overpressure. The analysis concluded that the only explanation fitting the facts was an internal explosion, and that a missile detonation hypothesis could not explain the observed toilet area damage. This is important because it shows what a genuine onboard bomb case looks like structurally: a clear local blast seat, concentrated deformation around that point, and breakup radiating from a confined origin. Now let's consider the MH17 case. A missile warhead produces a very different signature. In a proximity fused missile event such as MH17, one expects high velocity fragment penetration, directional external to internal damage, perforation and pettling of the skin of the aircraft, and recoverable warhead fragments. The physical evidence in such cases is characteristically asymmetric in the direction of fragment travel and leaves a clear external attack signature. Now let's consider the TWA800 case. The physical evidence from TWA800 differs fundamentally from both of those patterns. There is no identified missile-type fragmentation pattern, no warhead fragment signature, and no localized bomb-type blast seat comparable to the toilet-centered damage seen in the Atavia case. Instead, the debris pattern, the pack distribution, and breakup sequence are all consistent with an initial structural disruption in the center wing tank and pack bay region. In particular, the air conditioning packs provide an important structural clue, with packs 1 and 3 located outboard left and right, beneath or adjacent to the center wing tank, and they were found in the earlier red debris field, while Pack 2, located in the center line, remained with the later green main wreckage. This distribution indicates that the outboard portions of the lower fuselage separated before the central structure, which is consistent with an initial disruption in the centerline CWT pack bay region, followed by outward propagation across the lower fuselages. Let's have a look at the breakup sequence. The timing reconstruction adds an independent line of support. Using the last transponder return as the breakup reference point at 203112 EDT, with the aircraft at about 13,760 feet, a climb rate of 1,313 feet per minute, an estimated climb speed of about 303 knots indicated airspeed, and an estimated ground speed between 385 and 387 knots along the relevant debris tracks. The debris field midpoints yield the following sequence. The red zone midpoint, about 2031 20.9 EDT, or 8.9 seconds after the last transponder point. The yellow zone midpoint, about 12.4 seconds after the last transponder point. And the green zone midpoint, about 24.2 seconds after the last transponder point. This produces a coherent progression from the earliest impact, lower forward breakup debris in the red zone, then the forward fuselage and cockpit heavy debris in the yellow zone, and then the main wreckage mass in the green zone. That sequence is consistent with an initial structural failure near the center wing tank and pack bay region. Rapid shedding of forward and outboard lower fuselage components, and continued forward travel of the main airframe mass before final impact. The timing also matters because it supports a progressive internal breakup sequence, not the pattern expected from either a missile warhead or a compact onboard bomb. A missile warhead would be expected to produce an externally imposed fragmentation pattern and an immediate directional destruction signature. A compact onboard bomb would be expected to produce a more tightly localized origin, with structural evidence concentrated around that confined blast point, as in Batavia. The TWA800 timing and wreckage geometry instead indicate initial disruption in the center wing tank, followed by stage breakup and aerodynamic sorting of the debris. The three cases therefore show distinct physical signatures, and those are the mechanism and the characteristic signature. In TWA870, localized blast center confines severe deformation, breakup radiating from a discrete internal point. In MH17, fragment penetration, directional external to internal damage, perforation, petling, and warhead fragments. And in TWA800, a distributed structural failure in the center wing tank pack bay region, early lower fuselage breakup, no missile type fragmentation, no discrete bomb type blast seat. And TWA aligns with the third pattern, not the first two. Let's consider the question of what the witnesses saw, and there is no doubt they saw something unusual. And they did so under nighttime viewing conditions and even at a distance. The question is whether that observation is best explained by a missile or by the breakup of the aircraft itself. For both to be true, a missile strike followed by a fuel tank explosion, we would expect to see physical evidence of both events. A missile warhead produces unmistakable high-velocity fragmentation and penetration damage. Those signatures are not present in the TWA800 wreckage. A large fuel-fed fireball rising rapidly after an in-flight breakup can create the visual impression of an object ascending from the horizon, particularly at night and particularly over distance. This effect is not unique. In widely observed accidents such as Air India Flight 171 or the UPS Flight 2976, there were post-impact fireballs, and they were widely perceived as rising objects when viewed at a distance. What is observed instead in the case of TWA Flight 800 is a pattern of structural failure consistent with an internal fuel-air explosion in the center wing tank. A missile strike is not a hidden event. It produces distinctive diagnostic damage that can be identified in recovered wreckage. A common argument is that the key evidence may have been concealed or withheld. That possibility has to be considered. However, investigations of this scale, involving multiple independent organizations, including the NTSB, the FBI, the CIA, manufacturers, laboratories, and international experts, there were thousands of wreckage pieces that were recovered and catalogued and examined. Missile damage is not subtle. It produces widespread, high-energy fragmentation effects that would be expected to appear consistently across the entire wreckage field, and the materials analysis and the structural reconstruction. That absence is in itself a form of evidence. So, what is our conclusion? The combined structural and kinematic evidence does not support either a missile or a bomb hypothesis for TWA 800. A missile scenario would be expected to leave a clear external fragmentation and penetration signatures. A bomb scenario would be expected to leave a localized internal blast origin, analogous to the toilet-centered deformation seen in Atavia 870. Instead, TWA 800 shows a breakup sequence and debris distribution consistent with an initial structural disruption in the center wing tank, followed by outward propagation across the lower fuselage and staged in-flight breakup over the subsequent seconds. No missile signature, no bomb signature. A known fuel tank hazard, a flammable environment, a plausible ignition pathway, and a breakup sequence consistent with an internal explosion. When all lines of evidence are considered together, they point in the same direction. Accordingly, the available evidence is most consistent with an internal fuel-air explosion in the center wing tank, and not with a missile struck or a planted bomb. If a missile had struck the TWA 800, the wreckage would show unmistakable high-velocity fragment penetration. The available evidence does not show this. Thank you for watching, and if you like this investigation, please subscribe to ensure our work continues. Next Friday, we plan to publish an episode on the mid-air collision on the 29th of January 2025 between a Sikorsky UH-60L helicopter operated by the US Army and an MHI-RJ Aviation CL-600 operated by PSA Airlines as American Airlines Flight 5342. This accident occurred half a mile southeast of Ronald Reagan Washington National Airport at DCA. So please join us next Friday for that investigation report.